This is section 7.7, and we're going to talk about this section quite briefly. I'm actually working from pre-written notes here. Almost everything that's on this sheet is actually already written for you on the filled out notes that you have. And I'd just like to kind of talk our way through it a little bit to give you a feel for this, but there's very little that I'll expect you to be able to actually do from this section. There is one important calculator skill, though, that you're going to gain from this that we'll use again later in the semester, so it's worth spending at least a few minutes on. Our goal here is going to be to approximate the value of a definite integral. We're going to be using what we call numerical methods and also some technology here to do this, for the simple reason that we can't use the FTC. Why not? Well, the reason is, despite all of the techniques of integration that you learned in the first part of Chapter 7, there is no antiderivative for that function. There's nothing that we learned that would allow us to find an antiderivative, and in fact, quite simply, that antiderivative does not exist. So no matter how many techniques of integration you learn, there are always going to be functions whose antiderivatives we'll never be able to find because they don't exist. Antiderivative. There we go. All right, so what I'm going to do first is I'm going to say, let's just use a purely technology approach. You all know that you can get an integral numerically on your calculator. I'm going to do this one graphically because I'd like to see what this one looks like. So I've just gone ahead and put in the sine x squared in my calculator. And my window is set to -1 to 2 on the x-axis and -2 to 2 on the y. And there's my picture. I actually already did the integral, so it's already done in there for you, but I'll show you how I did it. I went to Second Calc and chose option number 7. My lower limit is 0, and my upper limit is 1. And in addition to drawing that for us, which you already saw, it gave me the value numerically of the integral. It is accurate to as far or as many decimal places as the calculator shows, but of course there would be more decimal places out here that we're not seeing and that the calculator perhaps has not calculated for us. So the question becomes, where does the calculator get that? And I'd like to show you a little bit about that. In order to calculate this, we need to use numerical approximations. And you already know one way to do a numerical approximation because we did it in Calc 1. And that was the Riemann Sum, where we use the rectangles to approximate the area under the curve. We saw this, and we saw how, because the rectangles aren't perfect, right, there was always either a little extra or not quite enough. So our estimate truly was just an estimate, not an exact value for the integral. Quick reminder of how we did that. This was our area formula. For each rectangle, we took the base times the height. The base, delta x, was b minus a over n. And I'm going to do an 8 rectangle, n equal 8 approximation. So for our purposes, that would be 1 minus 0 over 8, giving me a delta x of 1/8. The height, f of xi, the formula for xi is a plus I delta x. So in our case, the left-hand endpoint is 0 plus I times 1/8, or just I over 8. And so to approximate this integral, I set up my sum to go from 1 to 8, and I'm going to have f of I over 8 times 1/8. Plugging that I over 8 back into the original function would give me, whoops, that's supposed to be an 8, not an infinity. The sum from 1 to 8 of the sine of I over 8 squared times this 1/8 right here. Okay. All right, when I did this, and I'm going to show you how to do this in just a minute, what I did is this part that I have highlighted, I actually did that sum in my calculator to get the 2.914, etc. And then I multiplied that answer by 1/8 to get my final approximation. How did I get that sum? In your calculator's math menu, if you go down a little ways, oh, there it was, there is a summation option. That's what I'm going to use here. And I'm literally going to type in exactly what I wanted. Notice that the alpha is already on, so I'm going to go ahead and select the 1 here. Excuse me, not the 1, the I. Goes from 1 to 8. And then I'm going to type in my function sine of I over 8 squared. Sine of alpha I over 8. And I should have probably put in, I'm sorry, let me try that one more time. Sine of, I want parentheses around my I over 8 so I can square it. Alpha I over 8 squared. And then I can end the sign, and then end the sum. There we go. 1, 2, 3, open parentheses, 1, 2, 3, closed. I'm good to go. And there's that 2.914, etc. Okay, so that's really helpful. Calculator can do some sums for us. When I took that number and I multiplied by an eighth, notice that's where I got this 0.364. Okay. So using 8 rectangles, which is not a lot of rectangles, right? We got sort of a so-so answer. We got the 0.3 right, but we're off by about 5/100ths, so it's not a great approximation. I'm going to stick with n equals 8 for now, and we're going to look at some other ways of approximating to see if we can do better without increasing the number of rectangles. Right? The next way I want to do this is something called the midpoint rule. And what we do with the midpoint rule is instead of using the right endpoint to determine the heights of our rectangles, instead we use the midpoints. I've got that illustrated for this particular rectangle right here. Notice that the 2 left and right endpoints of the rectangle are here and here, but the height was determined right in the middle by this point I've labeled M, the midpoint. The advantage of that is the rectangle's a little too big on the left side, but a little too small on the right. So some of the extra kind of goes towards helping fill in the stuff I've missed. My delta x is no different, still b minus a over n, so still 1/8. But instead of using xi, what I'm going to do instead is I'm going to use the midpoint. And this is a formula right here for the midpoint. I take my right endpoint, xi, I add the previous endpoint, xi minus 1, and then divide by 2. In other words, I'm taking the average of this endpoint and that endpoint. And that's what's giving me the midpoint. Okay. Well, let's see. I know the right endpoint. That was a plus I delta x, just like last time. And then here's the left endpoint. Notice I just put in an I minus 1 instead of an I over 2. In our case, a is 0 and delta x is 1/8. Again, here a is 0 and delta x is 1/8. And so I get, let's see here, 1/8 times, excuse me, I factored out the 1/8. That's what happened. I took the 1/8 out here, and then I've got I plus I minus 1 over 2. 1/8 divided by 2 is 1/16 times 2i minus 1. I don't know where that square came from. Get rid of it. We just end up with 2i minus 1 over 16 for our m. So, going back to my sum, in each case then, I'm taking the height by plugging this midpoint, 2i minus 1 over 16, into my function, sine of x squared, times the base, delta x is 1/8. And once again, I went ahead and did this on the calculator. I put this sum in my calculator and got, after 2 tries because I screwed it up the first time, I got that value. So summation. And again, the alpha is already activated, so I'm going to say I, oops, goes from 1 to 8. There we go. And this time my function is sine of, and then in parentheses, I'm going to go with the fraction, 2 alpha I minus 1, oops, minus 1, over 16, close those parentheses, squared. And that ends the sine function, and the outer parentheses ends the sum. And there's that 2.476, etc. If I multiply that by 1/8, I get the 0.3095 and so on. Now, just a reminder, the original area on the graph, let me just do it one more time. Was 0.310. I'm now at 0.309. I'm only off by less than 1/100th this time, right? So definitely better than being off by 5/100ths. I've improved my estimate by using this midpoint rule. But still not great, right? It would be lovely if I could get, 3 or 4 decimal places worth of accuracy. There are better ways to do this, but they don't involve rectangles. They involve other shapes. I'm going to show you what I've done here, but I don't expect you to reproduce this next page. I just want you to see it. The next numerical approximation rule is called the trapezoidal rule. And what we do is, instead of leveling off like a rectangle, we actually draw a straight line from the height at the left endpoint to the height at the right endpoint. So we end up with that shape that I've got highlighted there, a trapezoid. Okay? The math is all here if you care to follow it, but I'm going to sort of say it, let's let it suffice to say that we did use the formula for the area of a trapezoid. Notice we plugged in a left endpoint and a right endpoint for the capital B and the little b. And we did all the math, and this time we got a closer answer. Notice I've got 0.311, and the exact value according to the calculator is 0.310 something. So I'm only off by about 1,000th now. Definitely an improvement. I can still do even better. Here's the most efficient rule of all. It's called Simpson's rule. And what it allows me to do is, instead of having to draw a straight line across the top, it allows me to use a little piece of a parabola along the top. So notice here, we've still got the left and right heights, just like we did for the rectangles or the trapezoids. But instead of drawing a straight line through the endpoints, we're allowing for a curve along the top. Not a perfect curve. It's not going to exactly follow every function because it is going to be a parabola. But by allowing the curve, our approximation gets a lot better. Here's the rather ugly form for calculating the value by Simpson's rule. Again, I'm not going to ask you to reproduce this. I'm simply going to tell you that when I did this for this problem, this is what happened. I got an estimate of 0.310248, etc. And notice what we've got here. 0.3102, 0.3102. The first 4 decimal places are actually accurate. And I've only used an n of 8. So, compared to the Riemann sums that we were doing before, where we only got 1 decimal place of accuracy when n was 8, this is a huge improvement. And I'm going to tell you that built into your calculator, computers, anything that does integrals numerically for you, is actually the Simpson's rule. It's by far the most efficient. They're, of course, using an n bigger than 8, which makes their accuracy even better. But they don't have to use huge n values to get decent accuracy when they use this best approximation technique called Simpson's rule. That's really all I'd like to say about this. The main skill that I'd like you to take away from this section is this idea that we can do sums on our calculator. I may have you play around with that just a little bit, but that's going to come back and we're going to use it again in chapters 8 and 9, so keep that in mind. Right. There's a bit more in your course pack about error estimates. If you're interested, by all means, feel free to read it. But again, I'm not going to spend a lot of time on 7.7, and I don't expect you to do a whole lot with it either.